When diving into the world of machine learning, one of the most crucial tasks is evaluating how well your model performs. For classification tasks, where the goal is to assign items into distinct categories, the confusion matrix is an invaluable tool. Despite its intimidating name, understanding a confusion matrix is easier than it first appears. In this video, we'll break down the concept in simple language and show you how to use it effectively. At its core, a confusion matrix is a table that allows you to visualize the performance of a classification model. It compares the actual labels from your dataset with the predicted labels generated by your model. This comparison helps you quickly see where your model is doing well and where it's getting confused. Imagine you have a binary classifier that distinguishes between two classes, positive and negative. The confusion matrix for such a model typically looks like this table. Each cell in this table tells you something about your model's performance. True positives, TP cases where the model correctly predicted the positive class. False positives, FP cases where the model incorrectly predicted the positive class when it was actually negative. True negatives, TN cases where the model correctly predicted the negative class. False negatives, FN cases where the model incorrectly predicted the negative class when it was actually positive. A confusion matrix is more informative than a simple accuracy score. While accuracy tells you the overall proportion of correct predictions, the confusion matrix breaks down the types of errors your model makes. This detailed view can be critical for understanding the strengths and weaknesses of your model, especially when dealing with imbalanced datasets where one class is much more frequent than the other. Medical diagnosis: in a test for a disease, a false negative FN might mean missing a diagnosis in a sick patient, while a false positive FP could mean unnecessary stress and treatment for a healthy patient. Spam detection: for an email spam filter, a false positive might send an important email to the spam folder, while a false negative might allow unwanted spam into your inbox. From the counts in the confusion matrix, several important performance metrics can be calculated. Accuracy: this measures the overall correctness of the model. Precision: quality over quantity. Precision tells you what proportion of predicted positives were actually positive. It's especially important in situations where false positives are costly. Think of precision as a measure of quality. Precision is about being precise in your predictions. Only claim a positive when you're really sure. Recall: sensitivity: don't miss a beat. Recall indicates the proportion of actual positives that were correctly identified. This metric is crucial when false negatives have serious consequences. Think of recall as a measure of completeness. Recall is about remembering everything important. Catch as many positives as you can. F1 score: the perfect balance. The F1 score is the harmonic mean of precision and recall, providing a balance between the two metrics. Think of the F1 score as the balance between precision and recall. F1 is the fusion of precision and recall. If one is lacking, the F1 score will drop. Each of these metrics offers a different perspective on your model's performance, and together they provide a comprehensive picture. To interpret the confusion matrix, we follow these 4 steps. Examine the diagonal. The cells along the diagonal, TP and TN, represent the correct predictions. A higher count here is a good sign. Identify the off-diagonal cells. The off-diagonal cells, FP and FN, show where the model is making errors. Determine which type of error is more critical in your context. For instance, in fraud detection, a false negative, missing a fraudulent transaction, might be more harmful than a false positive. Compute derived metrics. Use the formulas provided above to calculate accuracy, precision, recall, and F1 score. These metrics can help you compare different models or fine-tune your current model. Contextualize your findings, consider the cost or impact of different types of errors. Adjust your model or threshold based on what's more acceptable for your specific application. Let's say you've developed an email spam filter. After running your model on a test dataset, you obtain the following confusion matrix. Using the expression defined earlier, we can calculate accuracy to be 92.5%, precision is TP over TP plus FP, so about 94.7%, recall 90%, and F1 score is therefore about 92.3%. From these numbers, you can see that the spam filter performs well overall. However, the 10 false negatives indicate that 10 spam emails are slipping through. Depending on your tolerance for spam, you might decide to adjust the model to reduce this number, even if it means a slight increase in false positives. In many applications, your model might need to classify data into 3 or more categories. For example, imagine you're building an email classifier that categorizes messages as personal, promotional, or spam. In such cases, your confusion matrix becomes larger, a square matrix where both the rows and columns correspond to all classes. Let's consider a simple example with 3 classes, class A, class B, and class C. The confusion matrix might look like this. Diagonal cells 50, 45, 48. These represent the instances where the prediction matched the actual class. They are the correctly classified examples. Off diagonal cells, these represent the misclassifications. For instance, 2 examples from class A were incorrectly predicted as class B and 3 as class C. The basic concept of accuracy remains the same. It's the total number of correct predictions divided by the total number of predictions. In our example, accuracy is equal to 50 plus 45 plus 48 over 50 plus 2 plus 3 plus 5 plus 45 plus 5 plus 2 plus 4 plus 48 is equal to 143 over 164, 87.2%. For precision, recall, and F1 score, you calculate these metrics for each class individually. For example, for class A, precision for class A is similarly about 87.7%. Recall for class A is 90.9%. F1 score for class A is 84.54%. After calculating these for each class, you can average them using either macro averaging, simple average of the metrics for all classes, or weighted averaging, average where each class's metric is weighted by its number of true instances. Understanding the confusion matrix is a fundamental step in evaluating and improving classification models. As we've seen, it's not as mysterious as its name might suggest. Once you grasp its components and how to derive meaningful metrics from it, the confusion matrix becomes an indispensable tool in your machine learning toolkit. Whether you're working on a spam filter, a medical diagnostic tool, or any other classification problem, taking the time to analyze the confusion matrix will give you deeper insights into your model's performance. Remember, a good metric is like a mirror, it reflects what truly matters.